If you've ever written even a single line of code, you've been working with this hidden set of rules. It's a really deep, elegant structure that gives all our code its shape. And today we're going to gently explore what those rules are and, how they actually work.
I mean, it seems obvious to us, right? But have you ever really stopped to wonder how a computer knows the difference? Why does one version feel correct and the other just totally broken? It's such a simple question, but the answer is actually, well, it's pretty beautiful.
It's because underneath every single programming language, there's this invisible blueprint. And that blueprint is what separates a program that actually works from just, random noise. So let's gently pull back the curtain and see exactly how that blueprint is put together.
Okay, so let's get into the weeds just a little bit. When a compiler first sees your code, its first job is something called syntax analysis. You'll also hear this called parsing. It's really the very first step to understanding anything. Now, at this stage, it's not trying to figure out what your code means, not yet. It's just asking one simple question: is it structured correctly? And the main tool that makes all of this possible is something called a context-free grammar. Now, I know that sounds really academic, kind of scary, but trust me, it's just a simple but really powerful way to write down the rules for what a valid program is even supposed to look like. So, okay, why do we even care about this? Well, it turns out these grammars are incredibly practical. I mean, for one, they give language designers a precise, easy-to-understand blueprint. They also let us automatically build efficient parsers, that part of the compiler that checks the structure. And because the rules are so clear, they help us translate code, spot errors, and even make it way easier to add new features down the road. They're really the foundation of it all.
So to really get how they work, let's look at the basic pieces. And the good news is, there are really only a few simple components that make up any grammar. Okay, first up, we have what are called terminals. You can think of these as the basic words and symbols of the language. They're the things you actually type, like a plus sign, a number, the keyword if, or a parenthesis. And they're called terminals because, well, they terminate. You can't break them down any further. A plus sign is just a plus sign. That's the end of the line. Then, on the other hand, we have non-terminals. Now, these aren't the concrete symbols, they're the abstract concepts. They're variables that represent bigger structures, like an expression or a statement. You'd never type the word expression directly in your code, right? Instead, it's a placeholder for all the different kinds of things that could count as an expression.
And this right here brings us to the real heart of the grammar productions. Productions are just the rules. They're what connect our abstract concepts, the non-terminals, to the concrete things we can actually write, the terminals. A production rule is super simple. It just says, hey, here's one way you can build this particular thing.
So here's a great example of how all those pieces come together. This is a really simple grammar for basic math. The XB and op here, those are our non-terminals, our abstract concepts. And then all the other symbols, the plus, minus, star, the parentheses, and the word number, those are our terminals. The arrows show us the production rules. So that first rule, for example, is just saying an expression can be made of another expression, an operator, and then another expression. Simple as that.
Okay, so we've got our building blocks. Now for the fun part. Let's see how we can use these rules to actually build or check a real piece of code.
So this whole process is called a derivation, and it's pretty methodical. We start with our main high-level concept, like XP, and then we systematically replace the non-terminals with one of their options from the production rules. And we just keep doing that, step by step, until all we have left are terminals.
Okay, let's actually walk through one. Say we want to build this string here. We'd start with our main concept, exp. Then we can apply a rule to replace exp with exp op exp. Now, let's focus on that first exp and replace it with x parentheses to get our parentheses. Okay, now we're working inside the parentheses, so we replace that exp with exp op exp again. And from there, it's just a matter of replacing all the remaining non-terminals with the actual terminals, like number, the minus sign, and the star. See that? Because we successfully found a path from our starting concept all the way down to the exact string, we've proven that the string is valid according to our grammar.
Now, I know, this might seem like a really complex way to check something that looks pretty simple, but this is where the true power, the real beauty of grammars comes into play. It's all about their ability to handle infinite structures with just a few simple rules.
You've probably run into regular expressions before. They're great for simple, flat patterns, finding a keyword or validating an email, but they have one huge weakness. They absolutely cannot handle nested structures. Things like matching parentheses or nested if-else blocks, no way. That is a job specifically for context-free grammars, and the reason is recursion.
And this one little rule is the perfect way to see it. It says that A, our non-terminal for balanced parentheses, can either be an open parentheses followed by another A followed by a closing parentheses, or it can just be empty. Do you see how the rule refers back to itself? That's recursion.
So with this one rule, if we choose the empty option for that A in the middle, we can create a simple pair of parentheses.
And then, by applying that same rule to itself, we can get nested parentheses. And we can even use it to create combined structures. Think about that. This single, simple rule allows us to create an infinite variety of perfectly balanced structures. And that, right there, is something a regular expression just can't do. It's the secret to how our programming languages handle nesting.
So grammars are all about defining the shape and structure of a language. But it's also really important to understand what they can't do, because that helps us see the bigger picture of how a compiler actually works.
And it's worth remembering that the ideas we're talking about here, they're not just for people building compilers. As this quote points out, understanding this theory can be applied to a huge range of problems in software design, way beyond just this one area.
So here's the crucial thing to remember about what grammars don't do. They're context-free. For instance, a grammar can't check if you declared a variable before you used it. It can't enforce that your types match up, like you can't add a number to a string. See, those kinds of rules require context, and that's handled in the next stage of compilation, which is called semantic analysis.
So, if there's one core idea to take away from all this, it's this. Context-free grammars provide the elegant skeleton of a language. They define the structure, but they don't yet give it the full meaning. That part comes a little later.
And really, that's the quiet beauty of this whole idea. From just a few simple rules, you get a system that can create infinite possibilities. It's the elegant foundation that all of our complex software is quietly built upon.